In this presentation, we'll continue complex number operations when the complex numbers are presented in polar form. Here, we'll investigate division. You previously learned to divide two complex numbers in standard form. We'll now examine division when the numbers are presented in polar form. Let's define two complex numbers, Z1 with modulus R1, argument theta 1, Z2 modulus R2, argument theta 2. In class, we will show that you divide the moduli and subtract the arguments. Let's look at an example. Here we have Z1 with modulus 6, argument 40 degrees, Z2 with modulus 3 and argument 20 degrees. We divide. Notice the 6 is divided by the 3. Here we subtract the two arguments, and our final result is 2 parentheses cosine 20 degrees plus I sine 20 degrees. I would recommend you try problem 46 on page 696. Graphically, we can represent division as follows. Z1, which is represented in blue, has modulus R1 and argument theta 1. Z2 is in green, has modulus R2, theta 2. If you recall, we divide the moduli and we subtract the arguments. Our resultant will be the red point here for our complex number. Let's move on to finding the power of a complex number. Given a complex number z equals a plus bi, if we raise this to exponent n, and we were to do this when the complex number is presented in standard form, you see we'd have to expand these four binomials. The use of polar form will simplify the calculation. De Moivre's theorem states that when you raise a complex number in polar form to the exponent n, you raise the moduli to the exponent and then multiply the arguments by n. I want to emphasize that you pay special attention to the location of the exponent n in the result. Let's look at an example. Z equals negative 1 plus I radical 3. We want to find z to the 3. First, we must rewrite z in polar form to use De Moivre's theorem. The modulus r, we've calculated moduli previously using the Pythagorean theorem, and for this complex number it equals 2. The argument theta we find from the inverse tangent. It's 2 pi over 3. Recalling De Moivre's theorem, we raise the complex number in polar form to the third power. We raise the 2 to the third power and multiply the arguments by 3. Our final result is 8. Sine of 2 pi equals 0 and cosine of 2 pi equals 1. The resulting answer is a real number. I suggest you try problem 54 on page 696. We can also use De Moivre's theorem for finding the nth roots of a complex number. The nth roots of a complex number are given by these two equations. This is in radian form, this is in degree form. This is a more complex situation, and we will review this in class. If you wish, you can see examples on page 693 and 694. This concludes the videos for complex numbers in polar form.